In this video, we consider a quantitative analog of Rademacher's theorem called Dorronsoro's theorem. So Dorronsoro's theorem can be stated as follows. So first, we let f be a function w12 defined on Rd. And for such a function, we define an omega number. So given a point x and a radius r, we let the omega number be the infimum over all affine maps A, this L2 average difference between f of y and a of y divided by r. So geometrically, what this is doing is that it measures in a ball essentially the average deviation of f between an affine map, or how much f resembles an affine map in this ball. So Rademacher's theorem then states that the L2 norm of the gradient is comparable to the integral over Euclidean space of the integral from 0 to infinity of these omega numbers squared dr over r dx. Okay. In fact, Dorronsoro's theorem is more general than stated. He actually comes up with a characterization of WKP spaces for any integer k and any p between 1 and infinity. However, the case that we're going to be most concerned with will just be the W12 case. So for the work that we'll be doing, it'll be more convenient for us to work with a dyadic version of Dorronsoro's theorem. So I've defined an omega number for a cube q. It's defined in exactly the same way, except now I'm taking the average integral over a cube. And again, this measures the average deviation of a function f from an affine map, or how much f resembles an affine map over this cube. Then Dorronsoro's theorem can be restated as follows. The L2 norm of the gradient squared is comparable to the sum over all dyadic cubes q of the omega number of 3q squared times the Lebesgue measure of q. Okay, so it's a not too difficult exercise to verify that this definition is equivalent to the definition on the previous slide. Now, Dorronsoro's theorem was originally stated for W12 functions, but we have the following corollary for Lipschitz functions. So if I have a Lipschitz function between two Euclidean spaces, that's L Lipschitz, then for any dyadic cube R, if I take the sum of the omega numbers squared times the Lebesgue measure of q, where the sum is over all dyadic cubes contained in R, so that's what that notation means, then this sum is at most a constant times the Lipschitz constant squared times the Lebesgue measure of R. Okay, so let's run through the proof. So first, we notice the observation that the omega numbers are translation invariant in the sense that if I add a constant to a function f, that does not change the omega number. It does not change how well it's approximated by an affine map. So without loss of generality, I'm going to assume that when I evaluate f at the center of the cube R, that it's equal to 0. The next thing that we're going to do is truncate our function f. So we're going to find a function big F that's going to equal little f of x times the following function, the minimum of 1 times the distance from x to the complement of 5r divided by the side length of r. Okay, so what's going on here? So let's draw a picture. So here's the cube r. Now let's draw the cube 3r. This is 3r. And then finally, let's draw the cube 5r. Okay, so what happens when we have a point x inside the cube 3r? Well, then notice that the distance between this point and the complement of 5r is going to be at least this gap between the green cube and the blue cube. And this gap you can show is equal to L of r. So that means that this distance will be at least L of r. So when I divide it by L of r, this is going to be at least 1. And so that means that this minimum is going to be equal to 1, which implies that on the cube 3r, we see that little f is equal to big F on 3r. And then moreover, once x, if I have a point outside this cube, now this distance here is going to be 0. And so this function now is supported So big F is equal to 0 outside 5R. Okay? And furthermore, what you can show by our choice of function is that the Lipschitz constant of F is at most some constant times the Lipschitz constant of F, which is equal to L. Okay, so thus, let's look at this sum over dyadic cubes. So for shorthand, I'm just going to write Q contained in R. The context being clear that I'm summing over dyadic cubes contained in R of omega F of 3Q squared times the measure of Q. So notice that if I have let's use a color purple. If I have a cube, Q, that is contained in R, notice that its triple is always going to be contained inside 3R. And inside 3R, my function f is equal to big F. So this is going to equal the same sum, Q in R, over omega of F, or big F, 3Q squared, Q. All right, and then now this is less than or equal to the same thing if I just summed over all dyadic cubes. Which by Dorronsoro's theorem is at most the L2 norm of the gradient of big F. Okay, but remember, f is a function supported in 5R, and moreover, the gradient of f is at most the Lipschitz constant, which is at most a constant times L. So that means that this integral right here is at most some constant times the Lipschitz number squared times the volume of 5R, which is going to be some constant times the volume of R. Okay. So one thing that I should mention, so where did this hypothesis that f at the center of the square is equal to 0? So this comes into play when you show that the Lipschitz constant of big F is no more than some constant times the Lipschitz constant of F. And verifying that the Lipschitz constant of big F is at most Lipschitz constant of little f, I'll leave as an exercise for you to fill in. So one thing I haven't explained yet is why this is a quantitative analog of Rademacher's theorem. So recall that Rademacher's theorem tells you that at almost every point, your function is differentiable. Or in other words, as you start zooming in on a point, your function begins to look like a affine map. But it doesn't tell you how soon your function begins to resemble an affine map. However, Dorronsoro's theorem gives you explicit estimates on how often your function deviates from an affine map over all dyadic cubes. So notice, for example, that this omega number, recall that this measures how well your function resembles an affine map in the cube 3Q. This can't be uniformly bounded below by some positive constant as I range over all dyadic cubes, because then it would imply that this sum would be infinite. So what this estimate tells you is that, in fact, for most dyadic cubes, this omega number will be small. Or in other words, for most dyadic cubes, your function f looks approximately like an affine map. In the next video, we'll put Dorronsoro's theorem to good use and prove the lip by lip theorem.